So, are there any questions about the paper? Yes.
When you're like giving the figures sort of an orientation on the paper, I know I emailed you about this earlier.
Oh, about like the placement?
Yeah, the placement. I'm just having trouble because they're just all going to the end, pretty much.
Yeah, you know, that's hard. I know it's hard to do. And my advice, I think the advice that I gave you at the beginning was wait until the end when you have lots of text, and then try to place them. And the thing of it is that these figures are floating elements. So tech figures out where to put them based on your hints, whether they belong at the top of the page, the bottom of the page, or whether they occupy a full page. And so the only way that you can change the placement of it is to cut and paste your flowing text either above or below where you say to put the figure, and then tech will try to put it close to where that is. But it's difficult. And if they all get clumped, I think I gave you a guideline. I said don't have them all at the end, but if it's unavoidable, yeah, I don't want us to spend huge amounts of time trying to get that done.
There's actually a pretty good way of doing it. If you do bash clear page, it'll make sure that all the figures that are above it are placed before the clear page.
Oh, what's the command for that?
Bash clear page, and also creates
like this? CLEARPAGE, all one word?
Whichever one is the one you're meant to use for like sections, bash section, or is it just normal slash?
No, it's bash.
Okay, yeah, so then it's bash clear page.
Yeah.
Page. And then you can also do bash big break, which gives you like a space between two lines.
Yeah, sometimes I use bash page. Or is it page or new page? I don't remember now. I better not put it up.
Clear page puts a page break and also updates where the picture should be.
Yeah. Okay, so there's a tip. Yeah.
Does it matter? Like, I'm having problems with like making the graph look scaled properly. Because there's problems sometimes, like, I think when I took the PDF, it might have been like, basically like a rectangle, so like if I was trying to squish, like put two together and squish it into like two squares, it like looks a little funny and goes like a little bit past the header. Is that okay?
Yeah, let's not spend an inordinate amount of time making it look absolutely perfect. So, but there is a scale, when you include figures, there is a scale.
With the scale, and it did help in some cases, and then
Yeah.
sometimes it would like skew one.
Yeah.
The one would look normal. I don't know, I just need to.
Yeah.
But
Yeah.
I wanted to know worst case scenario.
No, you're fine. It's fine. Yeah, let's not worry about it. But I'll have to say, that the manuscript that I'm posting, all that's LaTeX, Z-LaTeX. And it looks, but it takes a long time. It takes a while to figure out how to do everything all just right. And I know for a first cut, it's hard. I know it is difficult, because basically what you're doing is you are having the tech code. It's like your source code, and your printed paper is the object code, and it's a compiler, and there's syntax, and you have syntax errors, and and then trying to get it to do what you want it to do is not always easy. And it's a steep learning curve, but I'm telling you, it's worth it. Man, once you get your document the way you want it, it's a beautiful typesetting for math and technical stuff. So math, physics, and computer science all heavily use tech. So that's why I think it's a good tool for you to learn. Any more questions before we go on? Okay, so at the end of class on Friday, I think it was, we had introduced the list, the BiTree-L project, which is the linked version of the binary tree, and we had done these pre-order, in-order, and post-order traversals, and we looked at the code for the pre-order traversal. So now, let's take a look at let's do some code walkthroughs and take a look at how some of these operations work. The first one is very easy in figure 8.8. It's is empty. So is empty is very simple. There's only a tree version of it, and as all it does is the by tree L : is empty. It has in its as an attribute a root, and as all it does is it just returns underscore root equals null pointer. So if the root isn't the null pointer, then it's empty, and if it's not, it's not. Yeah? So that's, and obviously you're not going to do, what would be an amateurish way to do this? If underscore root equals null pointer, then return true, else return false. All right? So don't do that. Slightly better, but still not as good, is return underscore root equals null pointer, question mark, true, false. Okay, but still, this is even better than that. Okay. And now, one that did not get exercised in the, for the user in the main program is left is empty. So there's a left is empty and there's a right is empty, because sometimes these algorithms are going to need to test whether the left is empty. So what happens is there's a precondition. If root equals a null pointer, then the tree doesn't have a left. So you can't test the left subtree of an empty tree. So that implements the precondition there. Otherwise, what do we return? So you remember it's underscore root arrow left. So how did that work? Remember it was like this in figure 8.3. So my by tree dot underscore root is a pointer to a node, and then the left, it's my by tree dot underscore root arrow left is the left pointer of the node to which it points. So that's how we test. So we return underscore root arrow left equals the null pointer. Everybody good with that? That's just a little short little one-liner. And I think we did demo this one. Root returns the root value, returns type T. But again, if the tree is empty, it doesn't have a root, okay, a root value, so we implement the precondition like this. So what happens, this is an example of that case where there is a tree version and a node version. Yeah, this is where we have a tree version and a node version of root. And so what happens is the tree version checks to see if it's an empty tree, and if it is an empty tree, it implements the precondition restriction. Otherwise, what it does is it calls the node version. Are you with me? It calls the node version of root, and then the node, because underscore root is a pointer to a node, so root arrow root parentheses is a call to the node version, and then the node version does what? Just returns underscore data, because what? Because in the environment of a node has an underscore data and an underscore left and an underscore right. Oh, now this next one is num nodes, number of nodes. Now here, I don't have a picture of this, I think, but look. Suppose this is a tree that's not empty. So this could be like 50, and this. Now, and this represents some subtree. And this represents, so this is L and this is R. This is the left subtree and this is the right subtree. And the question is, how many nodes are in this tree? Well, look, if it's an empty tree, so if this is the null pointer, then how many nodes are in the tree? 0, so it returns 0. Are you with me? Otherwise, what does it do? It calls the what? The num nodes method of a node. It calls the num nodes method for a node, and it does underscore root arrow num nodes. So now the code for it being here in this node. Now the question is, how many nodes are there in this tree? Well, there's obviously what? There's 1 for this plus what? However many are in here plus what? However many are in here, right? Is everybody See how that works recursively? Okay? But now here's the thing. This is the linked list version, so we don't know. This could be empty. I mean, this could be the null pointer. Are you with me? This could be nil. So look how we guard it. We say, so int result gets 1. If underscore left is not equal to the null pointer, now what do we know? We know that underscore left actually does what? Points to a node. You see how that guards it? That guards us not having a null pointer reference. Always with these linked ones, you guard. Are you with me? We guard it. So if underscore left is not equal to null pointer, result gets result plus underscore left arrow num nodes. So then that recursively calls however many nodes are in this one. And then it checks to see if this one is empty, and if this one's empty, it doesn't do anything to result. But otherwise, what does it do? It makes a recursive call to this and right arrow num nodes, and it adds that to result, and then in the end, the result contains 1 plus however many nodes are in this one plus however many nodes are in that one. Boom. Yeah? So everybody see how that works? And notice how you guard. Notice before you ever use, anytime you ever do a pointer, arrow, something, look in your code to see if you've guarded against it being nil. See, that's just a technique. Now, in figure 8.10, we have some definitions of some quantities that are used, that some of these functions compute. One of these, the one that's shown on the right-hand side of each tree, is the height. So notice that in part A of figure 8.10, it's a binary. We have a binary tree that only consists of just one node, and that's 60. And so that node is both the root and it's also a leaf. And we are going to define the height of that tree to be 1. And then in part B, there is a binary tree with a root of 40 and a left child of 20 and a right child of 65, which in turn has a left child of 30. And the height of that one is 3. And then in part C, the height is 5. So it's how many levels down you go. Now let me hasten to add that the height of a binary tree is not, the definition of the height of a binary tree is not consistent between authors. It depends on the book. And in fact, this definition of height is the same one that's used in our Greason-Schneider book that we used in discrete structures. All right, but it's actually not the most common one. You know, for example, if you take a look at part B, it actually looks like what's an alternate way to define the height? Instead of that height being 3, it's like what? 2. Like 2 stories high. You see what I mean? It's like, so with some authors, they define the height as how many levels you have to go up to get to the top. And so they would define that height to be 2, and they would define the height in part C to be 4.
And A would be negative?
And A, well no, and then actually that's a good point. So then what would A be? The height would be 0. But I don't like that definition, and neither did Greason-Schneider. Because using that definition, what's the height of the empty tree?
-1.
It would be -1, and that doesn't seem right. It seems like the height of the empty tree should be 0. So when we are talking about height, we're talking about how many nodes. We're talking about not how many jumps there are between nodes, but we're talking about how many nodes there are in the levels on the way down. Are you with me on this? And you know, when we developed all these algorithms and stuff, we had to deal with that difference, and we've decided to go this way. But it's actually, most people do it the other way. Not sure why, because this seems more natural to me, but some people do it this way. And then a leaf is a node with no children. So in part B, what are the leaves? Oh, it says there, 20 and 30. And in part C, the leaves are 90, 40, 50, and 75. So everybody sees, so that's the definition of height, definition of leaves. An internal node is a node that is not a leaf. And so the internal nodes in part B are 40 and 65. So the number of leaves plus the number of internal nodes is the number of nodes, right? Because a node is either internal or a leaf. Now, in figure 8.11 is, let's do a little code walkthrough of this. This is max. So the maximum, it returns, I think we demoed, did we demo this? Maybe not. Oh, this might be in the supplementary demo one. And then, so what happens, in order for a tree to have a max, it can't be empty. So the root version of max checks to see if root equals null pointer. If it is, it violates the precondition, and so it implements the precondition. Otherwise, it calls the node version of max. Now watch this. This code evolved over a long period of time. Now let me say, the third goal of this course is C++ programming, right? We all know that now. Okay? And let me say that there is a little C++ gotcha that is really tricky and it's obscure, and I don't want to go into the details of it, but this first line in the node version of max sets up a temporary variable called data temp, and the reason is because what max returns is a constant reference to t. You see, it says for this max function, what does it return? It returns a what? A t const ampersand. So it's returning a reference to t. All right? But now what is a reference? A reference is a what? Well, is an address. And what's a pointer? A pointer is an address. And there are some restrictions on using t const ampersand, and you can't do it. To do what we want to do in this code that follows, we need to use a pointer instead of a constant reference. And so this first line here is t, so look, what does it say? It says t const asterisk data temp. So what is data temp? It is a what to a what? A pointer to a t. Are you with me? Now what is a pointer? It's an address. And so do you see it gets ampersand underscore data. Now what is underscore data? That's the data part of this, that's the underscore data part of this non-empty node. I mean of this node. The only nodes we have are non-empty nodes. There are no empty nodes in the list L. Are you with me? So it's the data. So do you see that that's consistent with the types? It's setting one address to another address. And now what we do, and the reason for that is some obscure C++ thing. And now what we do is we use data temp now instead of using underscore data. That's the reason we do this, is so we can use data temp, because we can't use underscore data this way in the rest of this code. But what is data temp? It is a what to a what? It's a pointer to a t. So look what we do. We define, now what is left max? What is its type? It's also a what? A pointer to a t. So what we do is we say if left equals null pointer, then what is underscore left max? It's data temp. You see? So here, if there is no max over here, then what are we doing? We are setting left max to the what? To this. Do you see? But if there is a tree, if this is non-empty, you know, if this does have a max, then what are we doing? We're calling it recursively and returning the max of this to be left max. You see, this is calling underscore left arrow max recursively. Yeah.
Why is there an ampersand in front of left when you do left arrow max?
Because left arrow max returns a t, and that's the address of the t. Because left max is a pointer. They are both addresses.
So then like,
So we are dealing with the addresses of them.
so then is it like it's, I'm gonna scroll left arrow max and then the ampersand of that, or like?
Yes,
Okay.
it's what you said at the first, yes. All right? But basically what we're doing is we're saying, okay, so the max, if this is empty, then the max is just this one. If it's not empty, then the max is the max of this. All right, and then we're doing similarly for the right. So that was similarly for the right. So now what we're saying is, if this is empty, then right max is just this data. Otherwise, this is the what? Otherwise, right max is the what? It is the max of this tree, of this right tree. And now look what we have on the third line, on the next line. We have nested trinary operator. Are you with me? But why not? You see what we're saying? So look, there's one big trinary operator. So what's the first thing we check? We check if what? Now left max is a pointer. So what is star left max? That's what it points to. So there we're comparing the value. Are you with me? So we're saying return. So now what do we check? Star left max greater than star right max? What is that saying? Left max is what? Is bigger. So what do? We do this penultimate line. Otherwise what do we return? The last line. Are you with me? And you're following this logic? And so now let's look at the penultimate line. So if left max is bigger than right max, then what do we have to compare? Left max with what? With the temp. All right? And then if left max is greater than data temp, then star left max is what we return. Otherwise what? Star data temp is what we return. Are you with me? And we are returning an address because we're returning a reference to a T. And so the calling program can uses that address and accesses that value. So anyway, that's about as complicated as it gets, I think. Okay, so let's take a look at methods for construction and insertion. So in figure 8.12, we have a copy constructor is disabled. We have insert. I think we demoed insert root, right? That's how you build a tree. You make it with one root value. So precondition, this tree is empty. Postcondition, this tree has one root node containing data, so we give it data. And then set root. I think we did set root. That just changes the value, the root value. So the precondition is the tree is not empty. The postcondition is the root element of this tree is changed to data. And then I think we also did set left and set right, did we not? I'm pretty sure we did that. I'm pretty sure we demoed that. So set left is, the precondition is that this tree is not empty. Because, if we're going to set the left, we've got to have a left to set, right? And the postcondition is the left child of this tree is subtree, and the old left child of this tree is deallocated. And furthermore, once we set it to that, remember this is a cut set left, not a what? Copy set left. So it doesn't make a copy of it, it actually cuts it out, which means that what used to be subtree is empty. So subtree is the empty tree, is another postcondition. And similarly for set right. All right? And then for the rest of the figure, we have operator gets, and so that's the assignment operator. And as we did with the list, it's a deep copy of the right-hand side is returned with garbage collection. Okay, so it has to clear off the right-hand side. So if you say my tree gets your tree, if you say my tree gets your tree, like this, then what happens is the original my tree is cleared, right? So so it has to be garbage collected, and then a copy of your tree. My tree gets a copy of your tree, so that's deep copy. So that's not a cut operation, that's a copy operation. Okay, so let's take a look at the constructors. Now all of this stuff now should be, this is the second time around with all of this linked stuff, so this should be we should be getting familiar with this. So look, we have a constructor for the binary tree. Okay. And the binary tree has an underscore root, so when you set up a new binary tree, is all it does, what is this, colon, and then we postpone the brace, initializer list, so that's like saying what? Underscore root gets null pointer, right? Okay, and then for the node constructor, we give it data. So what it does is it sets underscore left to null pointer, it sets underscore data to data, and it sets underscore right to null pointer. So let's do a little picture here, a little sequence of snapshots to see exactly what happens. Now, do you remember what happens when we do a new on an object? There's three things now. What three things happen? Allocate storage from the heap.
Returns address.
Close, but that's the third. That's what happens if it's not an object with a constructor.
Go calls a constructor. Calls a constructor.
Yeah. Calls the constructor and then returns the pointer. Remember those three things. Are you with me on that? It's kind of, okay, are we good? So let's see what happens if we say P gets new L node T parentheses 70. Yeah? So in part A of the figure, let's suppose that P is our initial pointer. So now what's the first thing that happens with new?
It's called, like, it's the version of the heap.
Allocate storage from the heap. Okay, so allocate storage from the heap. So there's part B, there's the storage is being allocated from the heap. Are you with me? Now what's the second thing that happens? Call a constructor. But now does this constructor say? It says do what? Well, yeah, it says underscore left gets what? Null pointer, underscore data gets data, and underscore right gets null pointer. And our data is what got passed into the parameter, right? So what's the next picture look like?
72.
The 70, and so that executes the constructor. Are we good? And then what's the last thing that happens? It returns a pointer to that. And in this particular example, is P gets this. So what does P point to? That. So it returns the pointer and assigns it to P. Okay? So there's our constructor
Wait, is that
for a node.
Is that an actual value or is that a pointer to the value?
No, that's an actual value.
Actual value, okay.
Yeah. Because see, it says T data. Yeah. Good question, though, because we've been dealing with those references. Yeah. Okay. Now let's take a look. Let's take a look at insert root. So now what's our precondition? If underscore root is not equal to the null pointer, we're in trouble, right? So it has to be, you can only insert, remember when we did the demo, you can only insert root into a what? Empty tree. Are you with me? So what happens then, it does a throw -1. Otherwise, what happens? Underscore root gets what? New L node T data, right? So I think I have a picture here. So if you say my tree, so if my tree, now see, my tree in part A of this figure has to originally be what? The empty tree. So if you say my tree dot insert root 20, then obviously what happens? Underscore root gets new, and we saw what that does, right? So what does it do? It does this, part B. Everybody good? So that's how we do insert root. Okay. Now, this next one, figure 8.15, is an example of how of doing set root. So suppose that my tree has a root of 80, and 80 has a left child of 70 and a right child of 50, and neither one of those have any children. Suppose that's the original tree. And do you remember when we did my tree dot set root 10? Now the tree has to be what? Now the tree cannot be what? It can't be empty, and all it does is what?
Just change
Changes the what?
the consistent roots that
Yeah, so it changes the what to what?
the 80 to 10.
The 80 to 10. Yeah, that's all that does. Are we good? So that's the action of set root. Okay, and I don't think I even have the code for that. That's, or do I? Yeah, no, I don't. Okay, so that was a set root. Now, and I think we also demoed set right and set left because that's how we built our trees. Do you remember that? Okay. So, a precondition for, so this is the code for set right in figure 8.16. So set right says if root equals null pointer, so now if it's, how can you set the right of a tree if the tree doesn't even have a right? Yeah? So we implement its precondition by saying if root equals null pointer, we throw -1 with an error message. Otherwise, oh, by the way, you guys, I've noticed on your exams that a lot of people are still writing else here. Do you see why you don't have to write else? Does everybody, but anyway, on your code, do you see that the code, it's like having a return. You know, like when you have a return in the middle of some code, you don't have to do else, because once it returns, it'll return, it'll never get to that anyway. So this is, I think it's nice style to dispense with the else part there. Okay? But if the precondition is met, then what do? We do underscore root arrow set right subtree. Okay? And now let's take a look at the code for set right. So the code for set right does, the code for set right of a node does what? So now a node has a what? It has an underscore, it does have an underscore right. So now that we're programming a node, we can say if underscore right is not equal to the null pointer, then what do we call? We call clear, underscore right arrow clear. Otherwise, if it's already the null pointer, we don't have to clear. We don't have to do garbage collection. And what do? We do underscore right gets subtree dot root. So that makes underscore right point to what? The same thing that what? That makes that subtree underscore root is pointing to. Are you with me? And then what? Subtree dot underscore root gets the null pointer. So you know, remember it's a cut, right? So here's the figure. So let's suppose in figure 8.17 that we have these two trees. We have my tree and your tree, and my tree is pointing to the root of 60 with a left child of 20 and a right child of 40 and so on. And your tree is underscore root pointing to 80, has a left child of 70, right child of 50. And we say my tree dot set right your tree. Now what was that code that had to happen first? Here, let's go. What was that code that had to happen first up here in the? So if root does root equal the null pointer? No. No. So what does it do? It calls root arrow set right subtree. But then what? But then in set right subtree, what does that do? If underscore right is what? Not equal to the null pointer, what do we do? Right arrow clear. So what's the next? So what's the first thing that happens here?
40 and 10 get cleared.
The 40 and the 10 get cleared. Are you with me? And then the next thing that happened was what? Underscore
Right.
Underscore right does what?
Points to.
Gets.
Gets your
Yes, gets the subtree. So that makes, so it gets subtree underscore root, right? So your tree is the actual parameter, subtree is the formal parameter. Are you with me on that? Okay. And then what happens? Your tree gets null. So that just points in and boom, it's spliced over. Are we good?
You don't have to delete your tree.
Now you see your tree now, there's nothing, we see we're not deleting it, we're actually literally surgically moving it over. The thing that got deleted was the original my tree, the right of my tree. Yeah, so that's why we needed to clear for that. And here's operator gets. Now this is exactly the same code as operator gets for the list L1. The only difference is, instead of being copy root, it's what? What do we have for the list? You remember what it was? I think you wrote it. Instead of copy root, what was it? It was copy head. I think you wrote copy head.
Yes.
Yeah. So, but anyway, it's the same code, okay? And then return star this. All right? And now I have written copy root for you. So here in figure 8.19 is copy root. So the way the copy root works is, now, if the right-hand side is empty, then what do we return? Null pointer, right? Otherwise, what do we return? The root version of copy root. Are you with me? And so now that we're in the root version of copy root, we know there's at least one node, right? We know that there is at least one node. And so what we do is we do L node T star result gets new L node with the underscore data in it, okay, because this is a root, we're going to copy it, so with data in it, right? And then if underscore left is not equal to the null pointer, then we call result arrow underscore left gets left copy root, so that's a recursive call to copy the root for the left tree. And then if the right has something that needs to be copied, then we return result gets right. And by the way, if those don't get called, then that node got initialized with null pointers for left and right. See? And then we just return result, and that's it. Okay? And I think we can call it quits now. So then we just have a few more to do, methods for destruction and removal, and we can do those tomorrow.